Hi, SIwave is a power integrity and signals integrity tool. Compute frequency sweeps is one of the tools in SIwave, and it's the subject of this video. Compute frequency sweeps, which is this one, is used to study resonance in power planes. It is similar to the resonant mode solver discussed in another video, with a few differences. A frequency sweep solver detects resonance modes based on the physical dimensions and the effect of the source and the load. With the help of the circuit tool, which will be discussed later on, it's part of the Ansys electronic desktop, the frequency sweep solver injects the right voltage for each frequency based on the actual spectrum of the signal that exists in real life, in real use of the PCB. As a result, the frequency sweeps solver can determine the magnitude of each resonance in the proper way, versus the resonant mode solver only relies on the physical dimensions only. Let's start. It is not recommended to use SIwave to build PCBs. Although this is possible, it's not the best way to use SIwave. SIwave can import the following type of CAD tools. You can see the list here. Ansys ADB translator can be installed on Allegro and Altium to produce ADB files. OrCAD users are recommended to use the IPC 2581. Mentor Expedition users should use ODB++ files. Cadence users should generate board files and import them into the 3D layout, which is part of the Ansys electronic desktop. It's not part of SIwave. This requires Cadence to be installed, Extracta from Cadence also to be installed, and the path of Extracta from Cadence should be set in what we call the path environment variable. When you upload your file, SIwave extracts lots of information from the CAD file, including the stackup. See here, the materials, the components, and the nets. As a result, the model is ready for solving. After importing the model, the next step is to add sources. SIwave needs to know how and where each power plane net is excited. In SIwave, sources can be added in three ways: the DCIR setup, or what we call the net way. The second one is the manual way, and the third one is the component way. So what's the difference between these three techniques? Let's start with the first technique, the DCIR technique. Click on the orange mini icon you see here at the top left corner and launch the Configure DCIR drop analysis. That's why we call it DCIR way. The DCIR setup dialog box appears after selecting the DCIR. Next, the user must select a power plane or group of power planes and assign them voltage and current sources. So we start by selecting a net. That's why we call it also the net way, because we start by selecting a net. The voltage sources are assigned at the input, while the current sources are usually on the load side. So for example, I take this example 1.2. I will select a voltage source at the output of the VRM, voltage regulator, and I select the current source at the load. It is important for the user of SIwave to understand the concept of nets in SIwave. When you upload your model, the model may have so many nets, and some of these nets are connected in series using a component. If the component is a passive component, then you have what we call one passive link. These two nets plus the passive component represent one passive link. But if it has an active component between the two nets, then these two represent two separated passive links. SIwave can only solve passive links. So you take one passive link and you put a voltage source on one side and you put a current source on the other side, or you can put a voltage source on one side and voltage source on the other side. But it has to be a passive link. And that's how you read your schematic. You look for all the passive links that exist in the schematic. Going back to our setup. In this setup, what we are assuming is that at all frequencies, the voltage is 1.2. And the current source at the load is always 1 amp. So despite the fact that this is a DC setup, yet the same values will be used in the frequency sweeping. Now we proceed, we do configure simulation. This is simply allowing SIwave to build the ports and do the necessary setup. Validate is to check the physical structure of your PCB. Make sure all the nets are well connected. There are no problems, disconnections, anything unusual. As you can see, some of them, SIwave can fix them. It seems that we don't have any problem in our PCB. Now press OK. But we do not simulate because we are not interested in doing a DC analysis. We would like to do the frequency sweeping. We only use this setup to create our ports. So we can close this one. Now let's look at the second way of defining ports, which is the manual way. So from home, you select this voltage source and you have the current source. The problem with this approach, the manual, is that the user must know where the source is, as well as where the nearest ground is. By selecting 2 points, so let's zoom in, for example. For example, I want to create a voltage source from here to here. So I click voltage source from this point to the ground. By selecting 2 points on the PCB, SIwave recognizes all the nets under these 2 points. So it's very important to select these 2 points in the proper way. Any layer can be selected. For this application, for this case, both the voltage and the ground are on the surface. So I can press OK, it will create a voltage source for me. So that's how we do it in the manual way. Now, what about the third way, which is the component way? So we go to Tools, then we select Generate Circuit Element on Components. First, select the part number. Let's say for our case, it is the VRM, where we want to put our voltage source. If you have so many of them, then you have to select the reference designator. Now you have to select the pins. So in this case, it's pin 2 versus the ground 1. You can see here, you can have the reference terminal on another component. This dialog box is based on components. You start by selecting a component. That's why we call it the component way. Then at the bottom here, you select, you want a voltage source. Say create. And that's how you do it using the component way. Now that we have our voltage source and current source, we can go to the simulation and start running our frequency sweeps. So we give it a name, we give a solution a name. Notice here that you have 2 kinds of excitation, one using the source defined in the project, which are the voltage source and the current source, we just defined them, or there is the external way. We're going to show how we're going to use the external way later on in this video. For now, we would like to use the ones defined in the project. And this is the band where we are looking for resonance. We're looking for resonance from 1 megahertz to 2 gigahertz. In addition to that, we want SIwave to plot the field for us, the voltage between the surface area, for example, between VCC and the ground below, because we are looking for resonance in the power planes that are located in the VCC layer. And you launch. Now that we have a solution, we go to the results and we have the frequency sweep 1. And the first thing we'd like to do is view profile. This shows the solver timing and mesh used in each net. Different models can be compared using this information. And from there, the user can make a decision whether he's satisfied with the meshing or he wants more. Long runs can also be planned using this information. That's why it's important to review it. The second thing is the view simulation properties. So in the future, if you would like to come back and learn about the setup that created this solution. You can select this option, simulation properties. You cannot change it, but you can take a look at it. Now you know what kind of setup was used to generate this solution. Now we would like to see the results. So we select to plot surface voltages. The field can be plotted at any frequency on the selected layer. And we selected to plot the field between VCC and the ground. It's also possible to animate through all these frequencies. The scale goes up to 2.019, but the input, the injected voltage is only 1.2. This means that at certain frequencies there are resonances. Run the animation and observe where the high values occur to detect these resonances. We're looking for something that is yellow, orange, or red. Using this information, the user can place what we call voltage probes, as we're going to see later. Notice here some values, high values. Notice here more values, red values in this area. Notice here some red values. So now we know where to put our voltage probes. So the only way to do it is using the manual way. This is because the location of these voltage probes is not a pin, is not a connection between a net and a component. So you cannot use a net, you cannot use a component. It has to be done in a manual way. So this is our voltage probe. We will put a 1 here. So we set it between VCC and the ground. Probe 1. Let's put another one here. Same thing. And a third one here. Now we can rerun the solver again using the same setup. So now we have a second solution, but this time we're going to plot the probe voltages. So create plot, and this is the plot. See, that's the beauty of having voltage probes, is now you can detect the location of all the resonance. So what is the problem with this plot? It assumes that at each frequency we have 1.2 volt at the input and 1 amp at the output. As you know, this is not true. What you need to know is what is the resonance when you are exciting your PCB with the real voltage value at each one of these frequencies. So this is good to start with, just to understand what is going on. To change it, we need the help of what we call customized sources. And these customized sources are implemented using the circuit tool in the Ansys electronic desktop. So in order to do that, we need to go back to SIwave, and this time we want to do what we call S-parameter solving. To do that, we go back to our orange icon and we excite what we call the PI analysis solver. So the PI is the S-parameter solver in SIwave. And we select our nets again, and we assign ports this time. Instead of assigning voltage sources, we assign just ports. We set the impedance to 0.1 ohm. Configure, validate. Everything seems to be fine with the physical structure. And this time we will simulate. In the circuit tool, we will be using the transient solver. So don't forget to include the 0 Hertz. It's important to note that the maximum frequency, this one, number affects the rising time number, which is here. 0.5 over frequency is used to calculate the rising time. So we change this to 2 gigahertz. So the rising time now is around 250 picosecond. So that's the minimum rising time we're allowed to use with 2 gigahertz solution. So these 2 points, these 2 numbers are related. And we launch. Now we go to the electronic desktop. and we create a new project and we call it frequency sweep. And we save that to the same directory where we have our SIwave. Save. Now we add a circuit and we go here to symbols and we enter SIwave. So this is an SIwave link. So it's asking us which SIwave model or file you want to link to the circuit. We select this one. Now it's asking us which solution. So we have two solutions. It's the first one that we want. Has two ports. Now we add a voltage source at the VRM site. And we're going to select a PRBS source. And we add a resistor at the end. And we add a resistor at the output. One ohm. Now we set up the input. Remember we said that our rising time should be around 250 picosecond. Pulse width, let's say we want pulse width to be around 500 picosecond. The voltage to be 0.2 and not 1.2. That's our noise. Apply. Okay. Then we add a transient solution. XM, transient analysis. So the step here is related to the rising time. And the rising time is in picosecond. So it's 250 divided by 10. Let's select 25 picosecond. You can go even farther. The stop value is related to how many bits we would like to see. The longer this one, the better is the answer. So we'll select 100 nanosecond. Okay. And we solve. See solution. Plot 1. This is net number 2, and this is the ground is net number 3, or the zero ground net. So now we would like to display the results, and let's say VNet1, which is the input signal. As you can see, we have so many bits, 1001, 11001, because it's in PRBS. We also would like to display the spectrum of this signal. So we go back, same plot. This time we select spectral, VNet, and plot. So you see here, it shows you the spectrum contents of the signal. So that's why the longer, the more bits you have, the longer your simulation, the better, the more accurate is your spectrum. So the next step is to send back all this information back to SIwave. And the way to do that, you select this link and you say push excitations. It's okay. Now if you go back to SIwave and you select this solver, notice what happens now. It automatically knows that there is an external results coming from a circuit. It knows immediately. Launching the solver with the same setup. Circuit. So we change the name and we launch using the same setup. And we look at the results again, focusing on the probe voltages. So now we go back to the electronic desktop and we plot the probes versus the spectrum of the signal. Make sure to set them up to the same scale, 50 millivolt. Now you can see that this is a severe resonance because this is what we injected. This is what we are seeing on the power plane. Going back to SIwave, we can also plot the surface voltage. Now we can animate through the different frequencies. Now notice that the values are very, very, very small because the input voltage is very small. And what you see here is the real thing, because we are applying the right input voltage and the right output current at all frequencies. Let's compare these results with the results from the compute resonant modes. This solver was explained in another video, so we'll focus only on the results. So we launch the solver and we start from 1 gigahertz to 2 gigahertz. We want it to compute 30 modes, and we launch. Now we look at the results. So the resonant mode solver provides a list of resonances. To find the critical ones, the user must scroll through them one by one. To do that, you need to solve for the field between the two layers of interest, VCC versus ground, for all of them. Then you need to scroll through them one by one. The resonant mode solver detects a resonance at number 9, which is 1.268. So if we go back to the spectrum, we don't have 1.263, we have 1.26 and 1.27. And the resonant from the frequency sweep was detected as 1.257. So there is a small difference between the two. And that's the difference between calculating the resonance using only the physical dimensions, which is what the resonant mode solver is doing, or solving it using the physical structure plus the input and the output sources.